A transatlantic flight from Gander to Shannon requires crossing over 1,700 nautical miles of open ocean. For much of this transit, there are no alternate airfields available for an immediate landing. At any stage during this crossing, a mechanical failure or a medical emergency can force an immediate diversion. The sole objective is to get the aircraft on the ground as quickly as possible. This introduces a specific flight planning requirement, the point of equal time, or PET. Often called the critical point, this is the exact location along the track where the flying time to either the departure or the destination airfield is identical. The critical point dictates a binary decision for the flight crew. If an emergency occurs before crossing this coordinate, returning is the faster option. If the emergency occurs after, the aircraft pushes forward. The fuel loaded for an oceanic transit explicitly accounts for this diversion. A properly planned flight carries sufficient trip, contingency, and alternate fuel to reach a nominated airfield from the PET. Fuel volume is not a variable in this specific decision matrix. Here, vectors split from the PET toward home and onward airfields. The PET is a time problem, not a geographic distance problem. Because winds alter ground speed, the physical distance covered in that equal amount of time will be different in each direction. Assuming the point of equal time is the geographic midpoint of your route is a common mistake. In extended-range twin-engine operations, relying on a simple halfway point ignores the reality of wind components and ground speed. This diagram illustrates the mathematical architecture of the route. We define the total route distance as d. The distance from our departure point to the critical point is our unknown variable, x. This makes the remaining distance onward, d minus x. The speed variables depend on direction. H is ground speed returning home, while O is ground speed continuing onward. Since time home must equal time onward, we set the fraction x over h equal to d minus x over O. To isolate x, we cross-multiply, giving us x times O equals h times the quantity d minus x. Expanding the right side and collecting all x terms sets up the final calculation. Dividing by O plus h yields the simplified formula. X equals the total distance multiplied by the ground speed home, all divided by the sum of the ground speed onward and the ground speed home. This single equation is the required starting point for solving every DGCA exam PET question. In perfectly still air, your ground speeds onward and home are identical. As this first calculation shows, over a 500 nautical mile route, the math places the critical point exactly halfway at 250 miles. Introducing a 60-knot headwind drops the onward speed and increases the return speed. The formula now outputs a critical point 300 miles out, well beyond the halfway mark. Conversely, a 60-knot tailwind reverses those ground speeds, placing the critical point at 200 miles. These shifts reveal a consistent pattern. The effect of any wind component along the track is always to pull the point of equal time geographically into the wind. Identifying the wind direction allows you to instantly verify your math or eliminate illogical multiple choice answers before doing any calculations. If an engine fails, the aircraft must descend to a lower stabilizing altitude. At these lower levels, the true airspeed drops drastically. On this 2,050 nautical mile route, dropping the true airspeed from 475 knots down to 380 knots shifts the critical point by only 11 miles. Why does losing nearly 100 knots of airspeed result in such a small geographic shift? The location of the PET is controlled by the ratio of ground speed onward to ground speed home. When an engine fails, both absolute speeds drop, but their ratio to each other remains relatively stable. This leads to the most frequent error on the flight planning exam, determining the exact time to fly out to this engine-out PET. The time to the critical point must always be calculated using the all-engine ground speed. The aircraft operates normally right up until the moment of the hypothetical failure. Applying the anticipated emergency speed to the normal operational leg is the fastest way to fail the exam. Reduced speeds are only used for the escapes after the failure point is reached. Examiners will often provide wind velocity and track angles instead of pre-calculated wind components. A crosswind introduces a drift angle. To maintain the correct track, the aircraft must crab into the wind, which degrades its ground speed. You cannot solve this by simply adding or subtracting the wind speed. Because of the crabbing required, the tailwind component is rarely just the headwind component reversed. You must solve two separate wind triangles, outbound and reciprocal, to find the accurate O and H values. Relying on rules of thumb instead of strict vector geometry leads to incorrect ground speeds and compromised safety limits. Synthesizing this logic for oceanic planning, first, the formula architecture is x equals dh over O plus h. Second, the point of equal time always moves geographically into the wind. And third, always use the all-engine ground speed to determine the arrival time. Rigorously applying this math removes the need for frantic in-flight calculations. It ensures that if an engine fails halfway across the Atlantic, the decision to turn back or push on has already been made, providing a clear, pre-calculated path to the nearest runway.